Good evening, everyone. My name is Andrew Fracknoy. I'm the astronomy instructor here at Foothill College, and it's a great pleasure for me to introduce this evening's Silicon Valley Astronomy Lectures, co-sponsored by the NASA Ames Research Center, Foothill College, the Astronomical Society of the Pacific, and the SETI Institute. Our speaker tonight is Dr. Frank Drake, one of the most distinguished astronomers in the United States, who is popularly known as the father of SETI, the search for extraterrestrial intelligence. In 1960, Dr. Drake performed the first experimental search for radio signals from possible civilizations around other stars, thereby essentially founding the experimental science of SETI. And he's continued to search for such signals using both radio telescopes and visible light telescopes. With Carl Sagan and others, Dr. Drake composed several of the messages that humanity has sent out to the stars, including the Pioneer plaque, the Voyager audio-video record, and the radio message sent from the Arecibo Observatory, the largest radio dish in the world. Dr. Drake helped found the SETI Institute, the main organization involved in the search for life elsewhere, and has served as the Institute's president for many years. Now President Emeritus, he still serves as the director of the Institute's Center for the Study of Life in the Universe. He is also the former president of the Astronomical Society of the Pacific. Educated at Cornell and Harvard, Dr. Drake has been a professor of astronomy at Cornell, a professor of astronomy and dean of natural sciences at the University of California, Santa Cruz, and a director of the Arecibo Observatory. In 1961, Dr. Drake proposed an intriguing method of estimating how many intelligent civilizations might be out there for us to talk to, a method that has since become known as the Drake equation. Tonight, we asked him to update his thoughts about the Drake equation in light of recent developments. Ladies and gentlemen, it is both a personal pleasure and a professional privilege to introduce to you a visionary scientist and a great popularizer of science, Dr. Frank Drake.
Thank you very much for that very kind introduction, Andy. Andy and I have been partners for, gosh, I don't know how long, 25 years at least. And it's been a very great pleasure to work all these years with Andy. You're very fortunate to have him here at Foothill College. I guess they don't play, do they play football here? They do have a football team. And undoubtedly you have heard him on KGO and many other radio interview shows, where he always plays a marvelous role as a representative of the astronomical world and the world of education. Now, I'm here to talk to you about estimating the chances of life out there. And as Andy just mentioned, back in 1960, our civilization came to a threshold, a very important threshold, where our technology had advanced to a level where for the first time we could detect manifestations of intelligent life across the great distances which separate the stars. At that time, those manifestations were our radio and television signals, our radar signals. The signals we were then radiating could be detected by the radio telescopes, then primitive compared to those of today, from the nearest stars out to distances of about 10 light years. That led to the first search, which Andy just mentioned. And a year after that search, it led to the first organized attempts to give a scientific grounding to this whole subject, to give guidance as to what makes a sensible search, what the challenges were, what we would have to do if we were really to have a chance of finding extraterrestrial intelligent life. And as Andy mentioned, that actually led to a meeting at which a formula appeared, actually in a very simple way. It appeared as the agenda of the meeting with no feeling that this was of any great importance other as an agenda, but it has become, in fact, an equation which gives us both insight as to what we need to know to understand the challenges of our search, and what we need to know to design the equipment we do use to search for signs of extraterrestrial intelligent life. This equation is shown here in a pictorial form. I'll show it in a mathematical form in a second. The goal of the equation is to give you a number which will appear as n, which is the number of detectable intelligent civilizations in the galaxy. That is derived from an understanding of the history of the evolution of our galaxy, of the life of Earth and our technology, and the recognition that this can be quantified into a very simple equation, which is simply the product of 7 factors. It is based on the fact that our galaxy has existed for about 13.7 billion years. Stars have been created at an almost constant rate through the life of the galaxy, and this implies that stars, planets, life, intelligent civilizations, technology has also been produced at almost a constant rate. With that picture, one gets this simple equation. The first factor is the rate of star formation. The more stars you make each year, the more civilizations eventually you will have. You multiply that by the second factor, which is the fraction of those stars which have planetary systems. You then have the rate of production of planetary systems in our galaxy. Multiply that by the third factor, the number of planets suitable for life in each system, and you get the rate of production of potentially habitable planets in our galaxy. You go to the next factor where you see the butterflies here, and that is the actual fraction of such habitable planets which actually give rise to life. Multiply that by the fraction of those which eventually evolve in intelligent species. You have the rate of production at this point of the number of new intelligent species per year in our galaxy. You multiply that by the fraction of those which give rise to a detectable technology, and you then have the rate of production of detectable civilizations. How many are there? Well, we consider that once made, they become visible, we may detect them, but they may not last forever, for one reason or another. Perhaps there will be a cosmic accident, a great asteroid collision, which terminates the life of the civilization. Perhaps the civilization will collapse under the weight of its own growing population and such, and fail to manifest itself to space in a way we can detect. Most likely, at least to optimists such as myself, civilizations will come into view as ours is in view right now, but not stay in view forever because of increasing technological prowess. We have to detect things they waste, signals sent into space, power sent into space, energy which is wasted. And should they find ways to economize and to avoid that waste, a civilization can be thriving and yet undetectable. But this tells us that we must be careful about this and assume that a civilization, once being detectable, does not stay that way forever. And so this gives rise to the last factor, which has kind of a bad appearance here, the lifetime of a civilization in a detectable state. If we take the rate of production and multiply by that lifetime, we get that actual number n we saw in the first place. Well, here's the equation shown mathematically, including all the factors I just told you, the factor n, or the result n on the left, that which we are seeking, and all those other factors ending with L, the longevity of civilizations, on the right. And what you're looking at here is, in fact, a picture of a plaque at the place where this equation first appeared in a conference room at the National Radio Astronomy Observatory in Greenbank, West Virginia, where that first meeting in 1961 was held. And this was the agenda for the meeting. Now, in the 44 years since this came into being, our understanding of these values and what controls them, of these factors, has changed greatly. And that's what Andy wanted me to talk to you about tonight. What did we think 44 years ago, and what do we think today or know today in some cases where we knew nothing 44 years ago. And so I'm going to run through this and tell you what discoveries have been made, what clarifications have happened. And as you'll see, there have been some very important breakthroughs, most of them in a positive sense, that is increasing the possibility of there being intelligent life, and certainly some very important discoveries bearing on the nature and existence of life of all kinds, primordial and advanced and technological, in the universe. Now, as I said, the whole premise of all of this is that the galaxy has been producing new stars and planets for many, many years. Our sun is 4.5 billion years old, so not the oldest, not the youngest. And by the way, that's an important point. Everything about our system is usual. Nothing special that we have ever discovered about our system. We are not a freak system. The sun is an average star of average age. We have average amounts of chemical elements. Nothing special, nothing freakish seems to have been involved in our being here. We note in the galaxy the materials of planets, life, that is iron, carbon, nitrogen, oxygen, phosphorus, are made in the hearts of the stars and released into space as old stars explode, as you see here. There they join the gas and dust clouds of the galaxy, where the gas and dust clouds break off into little fragments, as you can see here in this picture. And some of them, this is a picture from the Hubble telescope, collapse even farther and in time become new stars. And back in 1961, we believed but did not know they became planetary systems. We had a theory. This shows the 3 steps in the theoretical understanding of how planetary systems come about. You start with a great cloud of dust. It collapses into a rather ragged disk, as you see in step 2 here, and in time becomes a flattened pancake. We see that more closely here. A star forms in the center. One gets a huge cloud of debris, which has become a pancake, and the little bits of stuff in the cloud of debris, as they orbit the central star, coalesce, join together to form ever larger bodies, which in turn collide with one another, sometimes disrupting each other, but in the long run, slowly accumulating into a small number of large bodies. Protoplanets, those objects which will become planets. There's a stage shown here, the T-Tauri stage, where, as it's called by astronomers, where this whole system ejects material at high speed out of the center. And this has been the theory, and in fact, this is well supported by observations, because we have seen now directly through photographs these disks of dust, disks of accumulating material around almost all of the nearby stars where it's possible to see them. Still, this was 44 years ago a theory with no observational support. Probably the greatest step ahead which occurred in those 44 years was the direct detection of other planetary systems. Clear evidence of the existence of planetary systems beyond our own, and in fact, planetary systems in large numbers, and providing us with so much information that we learn not only of their existence, but of the nature of planetary systems in general. And as you'll see, this has led to some really astonishing possibilities for life in the universe. Almost all of the discoveries so far have come by detecting very small changes in the position of spectral lines in the light that comes from the star, which is the parent of a planetary system. As a planet orbits a star, its gravity pulls on the star and causes the star to do a little wobble in the sky. As that star does the wobble, it introduces this very small Doppler effect, a very small shift in the position of the spectral lines. This has been detected, and from this one can deduce the presence of a planet, what its orbital period is, what its mass is. And in this way, and it's very difficult, evidence for the presence of, at this point, 152, an astonishing number, of other planetary systems have been detected. Most of this was done very near here at the Lick Observatory. This is it in a nice winter scene, using a rather small telescope, but an extremely powerful and sensitive spectrograph, which is really the heart of the discovery of these extrasolar planets. The small shifts in the spectral line are very hard to detect. It takes a very special spectrograph to detect them. This is one of the telescopes at Lick which is associated with the spectrograph. It's a 3-meter telescope. Many of you have probably seen it. It's many years old. It's not one of the largest by far, but until recently, its spectrograph was the best in the world. There is now a better one, made by the same person who made the spectrometer at Lick, and that one is at the Keck Observatory on Mauna Kea. Now we do know that these little wobbles in the spectrum are the result of planets orbiting stars. And we know that because now in several cases we have found that we are, with some of the systems, that the equatorial plane of the orbiting planet is lined up sufficiently with the line of sight to Earth that we actually see eclipses. We see the planet move across in front of the star, dimming some of the light in exactly the way one would expect if an object, say the size of Jupiter, passed in front of a star like our sun. Now, this is proof positive that what we are seeing is truly planets. No doubt about it. In fact, very recently, light from the planets themselves have been detected exactly as expected. And so there's no doubt at all that these 152 systems are extrasolar planets. That tells us that the fraction of stars which have planets, at least deduced from these observations, is at least 50%. It is probably more. The present detection system, this Doppler deviation system, can only detect very massive planets. So in fact, all of the planets which have been found are very large planets like Jupiter, 300 times the mass of the Earth, and recently down to Saturn and even to Uranus and Neptune masses, but very massive planets, and in most cases surprisingly close to their stars, contrary to what we might have expected. So what we have found so far is clearly the tip of the iceberg, in that we are finding the massive planets. The statistics show that there must be far more less massive planets than the massive ones we are finding, and those would be the terrestrial planets, planets like the Earth. They're there to be found. Our sensitivity is not there yet. So we look out and see objects such as this, giant Jupiters, some systems more than one, some of them orbiting very close to the stars. And the main point is that indeed there are planetary systems are not rare at all. They are very ubiquitous. They're present probably with at least half the stars, maybe many more, confirming those old theories of 44 years ago. Now, this is sunrise on one of those planets. I'm going to show you a lot of artwork today, all of it by Lynette Cook, who is a space artist in San Francisco that cooperates with the SETI Institute and many other organizations. Undoubtedly, you have seen her work in sky and telescope and astronomy, and she's been very kind to give me a large set of very recent paintings she's done for a book, which is just about to be published, and I'll show you the cover page for that book at the end of the lecture. But here's sunrise, just to give us an idea of what these other worlds might be like. You can see the star in the background, very large, because this is a picture that one would get with one of these Jupiter planets, Jupiter-sized planets, orbiting very close to its star. Now, so far the planets we have seen are not suitable for life, because we know Jupiter-like planets do not have solid surfaces. They're very hot inside. The constituents necessary for life are rare, or perhaps being destroyed all the time in the heat of these bodies. But we know that with these must be many, many small objects presently beyond our detection capability. For instance, these planets may have satellite systems, just as our Jupiter does. And those satellites, if large enough, and we have one in our system which is large enough, Titan, will have enough mass to hold an atmosphere, and although they may be satellites, they will have all the necessary constituents for life. Well, what are those? Very simple. Water, organic compounds, carbon-based compounds, and one of many sources of energy that are possible. Starlight, lightning, heat from just the interior of the planet, and so forth. And so we're beginning to glimpse the fact that there may be a greater variety of potentially habitable planets than our old ideas, which had it that only planets very much like the Earth could be supporting life. Now, 44 years ago, we had a concept which was very widespread, widely discussed, and which was probably one of the most wrong concepts in the history of astronomy. And this was the idea that for a star to have life, like the life of Earth, it had to be at just the right distance from its star. Just the right distance so there could be liquid water, because we thought liquid water was necessary for life. That meant it couldn't be too close to its star because it would be too hot, the water would all be evaporated. It couldn't be too far because then the water would be frozen, and we couldn't have liquid water to act as solutions for chemical reactions. And this led to the concept of what was called the continuously habitable zone. And all the astrobiologists who are here remember well the lengthy papers and discussions of the continuously habitable zone and the calculations which showed it was, in our system, in fact, very narrow, that the Earth just lucked out by being in it. There were controversies as to whether clouds would keep a planet warmer or colder and would change the habitable zone and so forth. Well, what we realized finally, and it was staring ourselves in the face all along, was that there were phenomena which made that whole concept almost meaningless. That there are ways for a planet at almost any distance from its star to be a habitable place. One of the prime ways that this was splashed in our face, was the planet Venus. Back again about 40 years ago, radio telescopes showed that the surface of Venus was at a very high temperature. This was a very strange result because Venus is almost a twin to the Earth in mass and composition. It's cloud covered at all time, which means that much of the sunlight is reflected, so the amount of sunlight it captures is almost the same as the Earth. And you would expect Venus to be at the same temperature as the Earth and to be a planet suitable for life. And yet the radio telescopes showed it wasn't at a temperature of, say, 70 Fahrenheit, but surprisingly about 750 degrees Fahrenheit. And it was in the early days at the National Radio Astronomy Observatory that I took this on as a project, and was amazed to find that when I looked at the dark side of Venus, it was just as warm as the hot side. The night side, and night on Venus lasts 116 Earth days, by the way. The night side was the same temperature as the day side to within 1 or 2 degrees. It took 80 hours of observation to establish that, by the way. It was a very difficult measurement. Subsequently, there were spacecraft landings, which showed that the surface was truly 750 degrees, that this wasn't some freakish radio emission that was confusing us. And we quickly recognized, actually Carl Sagan was pioneer in this, that this was caused by the greenhouse effect. What we know so well today is the greenhouse effect, that the atmosphere of Venus, with almost 100 atmospheres worth of carbon dioxide, has such a powerful greenhouse effect that it keeps the temperature very, very high. And what this means is you could move Venus way out in the solar system and the temperatures would still be high. You could put it way out and where it should be, much too cold for life, and it would be suitable for life. And this told us that a greenhouse effect can cause a planet to be a habitable planet over an enormous range of distances, just an enormous range. So an atmosphere can make a planet habitable and keep it habitable in a great variety of places in planetary systems. And then we discovered something else. The satellite Europa of Jupiter, which has an equivalent insulator to keep its ocean, if you will, suitable for life. In this case, the insulator is a layer of ice about 10 kilometers thick. This is two views of the same face of Europa. No craters because the surface is very young. It's made of water ice, 10 kilometers thick. Underneath that ice, there is an ocean of water. The outer surface of this object is about 170 degrees below zero. But that 10 kilometers of ice creates an insulating layer so effective that water can be in liquid state at a few degrees above freezing in the ocean of Europa, which actually contains much more water than the ocean of Earth. And this tells us then that here we could have life far out in a planetary system where the outer surface is extremely cold, and yet inside this, due to the insulating properties, the conditions are suitable for life. There's a third way this happens, and that is just the surface of a planet itself acting as an insulator. And the Earth is an example of that. Deep in the Earth, at depths of several kilometers, there is a great deal of microbial life, very ancient microbial life. And if the sun turned off, that life would exist here on Earth for billions of years, just kept alive by the heat flowing out from the interior of the Earth. So there's a third kind of insulators, solid surface, in addition to the liquid surface, or the ice surface, as with Europa, or a heavy atmosphere. And that's telling us then that there are many ways by which planets can be kept habitable in places which 40 years ago we thought were ridiculous. This is a picture of the ice on Europa, ice flows. We're looking at an area about 50 kilometers across, and you see the ice flows which have broken off, floated on whatever kind of slush or whatever is there sometime in the past. It's now frozen, but this is evidence that there is liquid water beneath the surface. Now, what this says is that in planets like Uranus and Neptune, they're like that. There can be places where temperatures are suitable for life. The outer surface may be at 150, 200 degrees below zero Fahrenheit. But as you go down in the atmosphere, because of the great greenhouse effect of the atmosphere, the temperatures go up and up. And in fact, we have observed directly with radio telescopes that there are layers in all of Jupiter, Saturn, Uranus, and Neptune where the temperatures are as in this room. And if the chemicals are right, you could even have perhaps life there. Now that's a speculation. There's no solid surface, there is only gas. But here's a concept of what are called floaters. Kind of cute. For some reason they have turquoise spots on them. That's the artist's idea. What you're looking at here is what could occur only not very far, about 10 to 100 kilometers below the surface of the cloud layer which covers all of these planets. And by the way, this idea is an old one. It was first suggested by Ed Salpeter and Carl Sagan at Cornell in the first paper on extraterrestrial life which was ever accepted for publication in the Astrophysical Journal, which was a real milestone because the editor at that time was a very conservative guy and talking about little green men and let alone floaters. Floating in the atmosphere of Jupiter was pretty far out, and it was. Now, stars like the sun, which again, 40 years ago we thought were the only place where you might find life. The more massive stars burn up their resources. They blink out too quickly to allow the evolution of any sophisticated life. That was our belief. We ruled out, actually, the great majority of stars, the M stars, the red dwarf stars. M stars called that by the astronomers. These are small stars with a mass about half that of the sun, but whose light is only a few percent that of the sun. And that meant that any planet of those stars would have to be huddled in close to the star in order to be warm enough to support life. And I guess you can already guess what's coming. A little greenhouse effect can take care of that, and they can be far out from the star and be warm enough for life. But there was another problem, which people thought was lethal to the idea of life on these stars. This is a conception of a Saturn-like planet orbiting a red dwarf star, glowing sort of a reddish color because the stars are red. There was another problem, and that is that if the planets were to huddle close enough to the star to be warm enough to have liquid water, the tidal force of the star would be extremely strong, and it would act on the star to cause the planet to keep one face to the star, just as the tidal force of the Earth keeps one face of the moon towards the Earth. And so it was felt that these would be very strange places with planets in synchronous rotation, one face towards the star at all times, and that meant one hemisphere of the star was in the dark, never got sunlight, starlight, became very cold, and this cold would freeze out the atmosphere and prevent them there from being an atmosphere, and therefore preventing the origin of life. Now, recently, it has been recognized through calculations that this isn't so. That, of course, the star will heat the sunward hemisphere of the star, and here's an artist's conception of it. But this will cause an air circulation, just as it does on the Earth, where hot air rises, flows, in this case, towards the terminator, the boundary between light and dark, towards the cold backside of the star, and would warm the star, and then there would be a reverse flow underneath the gases flowing from the hot side. And the end result, as it turns out from theory, is that in fact the cold side, the dark side, is kept warm enough that the atmosphere does not freeze out. And so in fact these things could in fact be habitable. Very interesting places. The star does keep one face to this planet keeps one face to the star. You may think there are two poles, but there's a hot place and a cold place, but these are not the poles of rotation. Those are at right angles to the hot and the cold place, so it takes a little getting used to. And what's wonderful about these when it comes to life is that you have a very hot region directly facing the star, and as you go towards the terminator, the temperatures become less and less. So there's a tremendous range of temperatures, and this creates the opportunity for there to be somewhere a zone where the temperatures are suitable for life, where there will be liquid water and life can evolve. And the artist has shown this here in the form of lakes, which are forming at just the right place. And you can see the clouds tracing the streaming gases from the hot point to the cold point. You might call these stars Camelot. The star, if you're standing in any place on this star where the star is in the sky, the star never moves. The star never sets, it never rises, it's always in the same place. There is no night. So if you're a living thing there, you live in quite a different way as we live here. If you move towards the hot substellar point, you get warmer. If you want cold, you want to ski, you go the other direction towards the terminator, and you can have anything you want. And it's totally predictable. Now, just to make this even more interesting, something has been revealed in those last 40 years about our system, which reveals to us a phenomenon which we had not guessed, and it was revealed to us by the planet Mercury. Mercury is close to our sun, and people thought it kept one face towards the sun, just as the moon does towards the Earth. But in fact, radar observations made at Arecibo some years ago showed to our surprise that that is not the case, and that as Mercury swings by the sun, in a very elliptical orbit, by the way, each time it is closest to the sun, it presents an opposite hemisphere to the sun. This is called a resonance. It comes about because of Kepler's third law, for those of you who know that, which says that in an elliptical orbit, an object, as it approaches the closest point to the star, moves very rapidly. Now, it not only moves very rapidly, but what's important here is that as it gets close to the star, tidal forces become very strong. The tidal forces go as the cube of the distance of the star, the inverse cube. And this means there's a tremendous tidal force on the star as it zooms by, on the planet, as it zooms by the star. And what happens is that tidal force tends to make the star, or the planet, keep one face towards the star whenever it passes close to the star. And to do that, it must spin at such a rate that it's not in synchronous rotation. And in fact, in the case of Mercury, it turns out that the balance point, where the torques due to tides are average out to zero in the course of an orbit, occur when the object presents alternate faces to the star, in our case the sun, each time it passes closest to the star. This could well happen to many, perhaps all, of the red dwarf planets, in which case there is no cold side to them. On each close passage, they will present an opposite hemisphere to their star, just as Mercury does. And this too will aid in evening the temperatures and making life possible. Now that's important because for every sun-like star there are almost 8 red dwarf stars. And so if now the red dwarf stars are perhaps more promising as abodes of life than the sun-like stars, it means the number of potential habitable planets has grown enormously in the galaxy. Now, this is a diagram that shows you how this works in a way. It shows you 2 of the newly discovered planetary systems superimposed on a diagram of our solar system. On the left is the system of 47 Ursae Majoris, which actually has 3 planets. One of them is very close and hidden in the image of the star in the center here. The planets are nearly circular, so this is very much like our system. On the right is the system of 16 Cygni, which has 2 planets, one in very close again and one of them far out, as you see, with a very elliptical orbit. This is the type of orbit that would lead to that phenomenon I just described to you of planets in the red dwarf stars presenting alternate faces to the star as they go by. But there's another point in showing you this, and that is that in the planets we have discovered, the great majority have very elliptical orbits, much more so than in our solar system. Now, that ellipticity is required to create the Mercury rotation phenomenon, but quite separately, it is evidence for phenomena happening in these systems which are very important. How do you get elliptical orbits when you start out with a disk of dust, as I showed you, where everything is rotating in very circular orbits? Well, what happens is objects collide with one another, and they make planets, and if you make enough planets, they will be orbiting in orbits close enough to one another that their own mutual interactions will perturb the orbits, alter them, so that the planets don't follow the same orbits all the time. And one has shown with computers that given enough time, this alteration of planetary orbits can result in one planet crashing into another or making a close passage to another. And the end result is the destruction of a planet or, and this is what's really surprising, the ejection of a planet from a planetary system. So what you see here is an artist's depiction of the sort of event which created our moon. A very large planetary-sized object crashed into the Earth, actually, and ejected enough material that it became the moon, and that's how our system came about. But had that object narrowly missed the Earth, it could well have been accelerated by the gravity of the Earth to such a speed that it would escape the solar system. And in fact, the computer modeling shows that this must happen very often. In fact, most of the systems we have found have as many planets as they can hold, and what's left there are in elliptical orbits. And this suggests that more planets than they could hold were created, and some of the poor, unsuccessful ones have been thrown out of the system to travel in the intergalactic space forever. An amazing thing. And in fact, there should be probably about one of these so-called runaway or rogue planets ejected from every system. And this can mean that there are as many lone planets, nomads of space, orphans of space, traveling in our galaxy as there are stars. and yet we have never seen one. They have to be there. We know they're there, despite the fact that we have yet to see one. Now, of course, that's interesting. You might ask, why haven't we seen one? It turns out it's very unlikely that one would have passed through the solar system during the history of mankind, and therefore it hasn't happened since we were here to observe it. But you could ask the question, could there be life on the rogue planets? And there are as many rogue planets as traditional planets like Earth. And your first thought was, of course not. They're sitting in the darkness of space for billions of years. How could there possibly be life there? But in fact, it could be. Here's an artist's conception of a rogue planet, or a runaway planet, far from its star, still very young, with lots of volcanic activity. And here again, our own system has revealed a phenomena which makes it so that rogue planets could support life. Now, probably not intelligent life, but primitive life. Now, how can that be? Well, we look at our Jupiter and Saturn, and we have discovered, to our surprise, that they release much more energy than they receive from the sun. In both cases, well, in the case of Jupiter, about twice as much energy as we receive from the sun. In the case of Saturn, 3 times as much. So the energy coming off from Saturn, too, is generated within Saturn, actually from a sort of helium rain, if you're wondering how. And only 1/3 is created by sunlight. So if you took that planet, made it a rogue planet, threw it out of the solar system, out into the interstellar space, so it no longer had sunlight, it would cool down, but it turns out not much, about 10 degrees. And this is after 4.5 billion years. There has been that much energy available from the interior of Saturn or Jupiter to keep it nice and warm for long enough to evolve life. So these objects, the rogue planets, and this is now shown very nicely, have enough energy coming from their interiors to keep them warm enough for liquid water for literally billions of years. And so even there are possible abodes of life. Well, I've spent a lot of time really on one factor here, which is the number of planets in each system suitable for life. And what we've learned in 44 years is that we didn't know nothing 44 years ago. There are all these other possibilities, and that the number of habitable planets is probably something like 10 times what we thought 44 years ago. Now, that's fine, but there's some other planets. I'll just mention them for completeness. Actual planets of terrestrial mass, which accompany pulsars, neutron stars. We don't think there's any life there, but it's kind of nice to look at their pictures because they're kind of pretty. They're bombarded with X-ray and gamma radiation, so they sort of glow in the dark, not through their own heat, but because of that radiation. But what about the Earth? In its earlier days, when it was very active with lightning, greenhouse effect, volcanic activity, or Mars, which in its early days had an ocean and looked something like what you see here. And this brings us to the factor in the equation having to do with the origin of life. What is the fraction of potential life-bearing planets which will give rise to life? Well, here we had good ideas. Even 44 years ago, there had been experiments done in which we simulated conditions in samples of the primitive atmosphere of the Earth as we believed it to be then, and as well as atmospheres simulating the atmospheres of other planets such as Jupiter and Saturn. You take a mix of chemicals, carbon or methane, carbon dioxide, water, CO2, you put them in a flask, introduce energy, in this case an electrical spark, see what happens. And what happens is you create large organic molecules, and in particular the basic chemical building blocks of life. Now, it doesn't take much to make life as we know it here on Earth. Actually, only 28 building blocks. You just need 28 parts bins. You need 5 purines and pyrimidines, 20 amino acids, sugar, deoxyribose, phosphate, and water, and that's all it takes basically to make life. Of course, not sophisticated life that invents other things that make things much more useful. But basically, that's what you need. And all of that stuff is cooked up in these kind of experiments, always. And this has said that there are many, many chemical pathways to life in a primitive atmosphere like the Earth. Now, the old idea was that these got captured in the ocean and created a sort of primordial soup. There was nothing living to eat it, so it stayed sterile, it didn't spoil. It just got thicker and thicker and thicker. And Darwin himself proposed that this would accumulate in what he called a warm little pond, and the chemicals would react, and out of it would come living things. Now, just what happened has been probably explained a little, in a way, more closely to the truth by our DNA analyses of the history through time of the evolution of life on Earth. This is the tree of life, the famous tree of life, which has three branches: the bacteria, the archaea, and the eukaryotes. We are at the very top there on the left, the animals, the most sophisticated, with the most complicated genomes. As you go back down this tree, you go back in time, and when you get to the very bottom, you see a word there, thermophiles. That means friends of heat. And these objects, they're very primitive microbiology, are things which like very high temperatures. They live at temperatures of boiling water, for example. And this suggests then that the warm little pond wasn't just warm, it was really hot. And where do we find that on Earth? We find it at the black smokers, the hot deep sea vents in the ocean. And all of this supports, it's in a funny way, a smoking gun, there it is, that life was born at the deep sea vents. This is somewhat controversial. There's some thought that it was born in colder water and migrated to the deep sea vents because they were so full of nutrients, and maybe that's so. But in any case, this is good news, because in any water-covered planet, we can expect deep sea vents to be there, and therefore life to arise. And what this has said is that the fraction of potential life-bearing planets that give rise to life is probably 100%. We're looking now, or will look soon, for life underneath the surface of Mars to see if that insulating surface has kept temperatures suitable to keep life alive at the necessary depth, which isn't that far down. It's 100 meters or so down, where water would be liquid on Mars. Not far down for us on Earth, but very far down for any kind of spacecraft to dig, and that's one of NASA's great challenges. Now, what about F sub I, evolution? This is the most controversial, still, part of this whole subject. There are paleontologists that look at the fossil record, look at our Earth today, and make what I think is a dreadful mistake. I'll be right up front with you about that. They look at Earth and they say, oh, there have been literally hundreds of millions of species in the history of the Earth, and only one became intelligent. Doesn't that mean intelligence is rare? Well, that has to be wrong. And I can tell it to you in a way which I think you will accept. Life, clearly it takes a good length of time to evolve an intelligent creature. We're very sophisticated, we need big brains, we need very large biological, physiological structures to handle or to produce intelligence. So it happens slowly. In our case on the Earth, it took 4 billion years for intelligence to arrive. But there is certainly not just one path that can lead to intelligence. There may be many paths leading to intelligence, an intelligent creature, different species, but they won't all arrive there at the same time. One of them will arrive first. And so in every planet, at some point, there will be just one intelligent species. That's the only way it can be. And so when that intelligent species is smart enough to look around and know something about intelligence, it shouldn't be amazed that it's the only one. It's the only possibility. And if any of you want to argue with me about that, I would be glad to, but I think that particular argument is pretty strong. The fossil record supports this, by the way. It shows that there's the one thing that has always increased in the fossil record is the size of the brain. So being smart is good for you, it tells us. And here's an example of one creature that was on its way to being intelligent, perhaps before we became intelligent. It's a dinosaur. Its name is Stenonychosaurus inegalis. I hope you all got that. That's going to be on the quiz in that astronomy course that Andy was talking about. Or it's a $1,000 question on Jeopardy, if you're ever on Jeopardy. Stenonychosaurus inegalis. It was about our size, weighed about 100 pounds, stood about 5 feet tall, could grasp things with its forepaws. It was bipedal. It even had binocular vision, which was very rare in dinosaurs. But most interestingly, its brain was much larger than was typical of 100-pound dinosaurs. 100-pound dinosaurs actually had brains about the size of a pea. They were really dumb folks. But not this one. This one had a brain whose brain mass was approaching that of a human infant. And so it has been speculated, it lived, by the way, 65 million years ago. It has been speculated that had it lasted a few more million years, it might have evolved into what you see in the foreground here, the first intelligent creature on Earth. And this would have been your mother and or your father and your boyfriend or your girlfriend. And you would have loved them just the same. But that was not to happen because, this is courtesy of Professor Morrison, who is sitting here in the front row. He's the godfather of doom on planet Earth. Well, he is known as Dr. Doom at the NASA Ames Research Center. He's the expert on asteroids that collide with the Earth. And 65 million years ago, a 10-kilometer asteroid did collide with the Earth and created a tremendously devastating event, spraying molten rock all over the Earth, set the Earth on fire, created a cloud of dust which lasted for months, killed all the large, or disrupted the food chain so terribly that all the large creatures on Earth perished, and with that went those dinosaurs. This is what a really mad dinosaur looks like. And here comes the fireball, and what do we do about it? When the great catastrophe was over, the dust settled, and finally the sun came out again. There were some creatures who had made it through the long night. They came crawling out of holes in the ground, out from under logs, and they were our ancestors. They were little shrew-like characters, the mammals of that time. The largest mammal you could be. If you're any larger, the dinosaurs ate you. But now they weren't there anymore. And so you could grow and become big boys and girls. And 65 million years later, them is us folks. Well, I think that story says that given enough time, you will get an intelligent species. But as I said, this is still controversial. Still controversial. Now, on Earth, as soon as you had an intelligent creature that could manipulate tools, namely us, technology appeared independently in at least 5 places. And this tells you that intelligence quickly learns to use its physiology to become a tool maker. And it's only an instant in cosmic time from the simplest tools to motorcycles and videotape recorders, automobiles, jet planes, and all the rest. All of that has happened, as you know, in something like 1,000 years out of the 4 billion year history of life on Earth. So that tells us that the F sub c, the fraction which develop technology, is very large as long as they can manipulate tools, which probably means they need to be land animals, probably not intelligent creatures in the sea. So we have things such as this, the Arecibo Radio Telescope, and other civilizations can have this too. This, by the way, is the strongest sign of our existence on Earth. It has a 1 million watt transmitter and that large sort of hemispherical thing you see in that slide and in this one. And that 1 megawatt, 1 million watt transmitter's power, when concentrated into a narrow beam by the big dish, creates a beam so powerful that it outshines our sun by not a little bit, but about 1 million times within the frequency band of the transmitter. That signal is detectable by another telescope like our own from a distance of the far side of the galaxy. So from any civilization in our Milky Way which has a system like this pointed at us, we can detect it. This has just recently been upgraded for use in SETI. It now has 7 beams and is by far the world's most powerful instrument for searching for signals. The only problem with it as a SETI detector is that it's used for other things and is only available to SETI in essence a few days a year, although it is used regularly to capture the data that's used in SETI at home for those of you who use that system on your personal computers. So we are an example of an intelligent civilization. This is what the large bowl at Arecibo looks like. And if we look at ourselves and use ourselves as a model, which is all we can do, we have been detectable for about 50 years. And now I'm addressing that very last factor in the equation, the L factor, the longevity. We have been detectable for 50 years, primarily through our television and radar transmissions. How long will that continue? We wish we knew, because that is the key factor, in, as we'll see in a minute, in estimating the number of civilizations to be found in our galaxy. This one is the big unknown. And unfortunately, we cannot know what it is till we found another civilization, because we don't think we can use ourselves as a model. We're too much in the beginner phase. And in fact, we already see signs in our civilization of our civilization heading towards becoming less visible or perhaps even invisible, that our longevity as a detectable civilization may end much sooner than we expected. For example, this is really scary to people like me. What is this? You've all used it, you just didn't know it. This is a synchronous satellite which is used to transmit television programs to Earth. It's used for DirecTV, Dish Network. It's used for the old large dishes. It's actually used these days to transmit even cell phone messages to and from the Earth. And why is this bad news to people like me? Well, as I just mentioned, Arecibo transmits 1 million watts. The typical conventional television transmitter, as you find on Sutro Tower in San Francisco, transmits about 3 million watts. In fact, there's 30 million watts of power comes out of the Sutro Tower in the form of television programs. That is the main sign of our existence. But what comes out of one of these? It's beamed carefully down on the Earth. Here's the actual parameters, and if you look about halfway down, you'll see the KU band payload. That's actually the channels that are providing the signal to the little dishes. Many of you have the 18-inch dishes. And what's the power? 75 watts. And not, much less than 1 million watts or 3 million watts. You see some others are 20 watts. And that's all it takes to send a signal from 22,000 miles above the Earth to a little 18-inch dish on your back porch or whatever and give you a very fine television picture. It's one of the most amazing developments in the history of technology. Not only that, this is the pattern of the radiation as it's directed on the Earth from the satellite. You can see they actually are capable of tailoring it so it matches the contours of the places where the people are that pay the bill for the signal. It matches the continental United States. You see a little finger reaching out to Puerto Rico, another one to Hawaii. And this is brilliant engineering. But for us, very bad news, because not only is it only 75 watts, but almost all of that falls on the Earth and is absorbed. The actual power going out into space is probably not more than 10 watts. And that's a lot less than 1 million. If this becomes the way to transmit television, the Earth will become much harder to find. But we search. Another thing is the cell phones. Affordable even by poor people all over the world, and they radiate a power of only a few watts. and yet they work. We don't need high power to make that work. Again, a step in the development of our civilization leading to less visibility. So what this says is, well, we don't know what L is. We can only guess. We might guess there are other things which will keep L a large number for a long time, but we don't know what those are. I'll show you a couple of examples, possible examples in a minute. But that allows us now to take a look, finally, at where we stand today. Now, this is actually a page that I did not invent. It's actually from the notes for a course at the Pennsylvania State University. I just picked it because it's an unbiased estimate of all the factors in the equation. You can see them here. Mean rate of stars, 1 to 10 a year. Fraction of stars, 0.1 to 0.5. I mentioned 0.5. Number of Earth-like worlds, 1 to 3. That's about what I said. Fraction of those where life develops from 0.1 to 1. I said it was about 1. Intelligence, somewhere between 1% and 1. So on. The lifetime here estimated at much more than our experience, 10,000 to 1 million. Well, if you multiply these all together, what do you get? Well, I want to show you an abbreviated version of this. If you take the most likely numbers for the first 6 factors, they all multiply together very conveniently to a number close to 1. And this makes it easy to abbreviate this equation into something much easier to remember. You can even put it on a California license plate if you want. Mystify all your neighbors. What does that mean? N equals L. It's telling us that as best we can guess, and guess is the right word to use, the number of detectable civilizations is equal to that longevity, the length of time on average they stay visible. Now you may wonder why this is written in such fancy letters, and the scientists here know the answer to that. It's then when you don't really know something well in science, it makes it more believable if it's written in fancy letters. So N equals L. Well, what is L? We don't know. And unfortunately, people keep coming up to me and asking me, when are you going to succeed? When are you going to succeed? And I used to say by the turn of the century, but that was about 10 years before the turn of the century, and I found out that was embarrassing because pretty soon the turn of the century was there and we hadn't succeeded. So the right answer to this question is, in order to know how soon we will succeed, we need to know the value of L, but to know the value of L, we have to have succeeded. And if you say that real fast, it sounds sensible. But if that is not satisfactory to the questioner, and they say, wait a minute, so, okay, what is L? When are you going to succeed? Then the fallback answer, the desperation answer is soon. Now, soon is not very well defined scientifically, so you weasel out of it in that way. Don't ask me what soon is, but soon is the answer to that question, in case any of you are tempted to ask me that. Well, what should we search for? I've mentioned that we've been searching for radio waves. We could search for the lights of cities at night. This is a mosaic of photographs of the Earth at night taken from satellites in space. You can see the northern lights up there on the upper left-hand side. Over on the far right, the brightest country is Japan. Any of you who've been there know that they love to put all kinds of bright lights on their buildings at night. You see some strange things, some lights in northern Siberia, which are the waste gas from the oil fields being burnt at night. Same thing in Saudi Arabia. Here's the United States at night. If you've got good eyes, maybe you can find your house. I think you can probably find the Bay Area there, and you can see, in fact, Route 80 stretching from the Bay Area to Sacramento. And you can see Route 5 going all the way up to Portland and Seattle with little cities looking like beads on a string along the way. Well, it turns out it would take an optical telescope about 5 miles in diameter to see the lights of cities at night. So we're not going to do that now, but it's possible other civilizations do, and they know all about us because they have been able to build such large telescopes in space, undoubtedly. or they have used their own star as a gravitational lens to make a giant telescope. You can do that. It makes a telescope with a lens equivalent to the diameter of the star, about 1 million miles. So it's a very powerful instrument. You can actually resolve cities on the planets of stars 100 or so light years away. And you might ask, why aren't we doing that? And the reason is the focus of the lens, if it's a star like the sun, is about 500 astronomical units from the star, which is about 10 times the distance to Pluto. So it's not doable by us yet, but it's in our future. And it could well be that this is the standard way to detect and study civilizations. You use the stars as gravitational lenses. Radio, this is what we used in the first search in 1960. It was an 85-foot telescope at Green Bank. Here's the equipment. Not a transistor or computer to be found. It was 44 years ago. But for those of you who are old enough, you will recognize over there on the right side a Wollensak tape recorder, which we had attached to the equipment so that we could record the voices of the extraterrestrials when we captured them with our big radio telescope. This monitored one channel at a time. It was used to search for signals from the two stars nearest to the sun that are like the sun, Tau Ceti and Epsilon Eridani, for 2 months. No signals from those stars were heard. Signals were heard, but they were from us. We've graduated to larger things, such as the Arecibo telescope, 1,000 feet in diameter, with radio receivers, which are far more sensitive than we had 44 years ago. In fact, this telescope can duplicate all of that first experiment, all 2 months' worth of the observations, in about 1/10 of a second. That's all it takes. So you wonder maybe why did we do that? But you've got to start somewhere. Today we've graduated to the use of sophisticated computer electronics, which allow us to observe not just one channel at a time as it was in 1960, but rather today we observe 100 million channels at a time. And at Harvard there is now a system which can observe about 250 million channels at a time. And in our new system at SETI Institute, we will be observing 120 million channels at a time. This is a typical screen, lots of noise. Each horizontal line here is 1 second's worth of data. You see a slanty line. That is the most distant intelligence signal ever captured. It was captured from the Pioneer 10 spacecraft, which is at the edge of our solar system, radiating a power of about 5 watts, about the same as a cell phone, from a distance of, we still observe it today. This was earlier, a couple of years ago. We observe it today at about twice the distance to Pluto, and still easily detect that signal. It just shows the power of the radio telescope to detect very faint signals from very great distances. What else might we be out there? Maybe creating greater longevity, greater L values, space colonies. Might it be that this is what we detect? Colonies in space radiating to their home planet, to other space colonies. It's things like this which we can only wonder about, things which can exist and which could create or maintain the visibility of civilizations for much longer time than we might presently imagine. It's even been hypothesized that there is a galactic internet of interconnected civilizations with their interconnected beams, transmission beams, shown here as a sort of a spider web of energy going across the galaxy. So, although we see our own planet perhaps becoming fainter, perhaps there are other things which keep civilizations visible. Things like this, perhaps solar power stations in space, who knows? We do need to do a great deal of searching, particularly in the radio. So far we have searched 150 light-year radius from the sun, and this diagram gives you a slight feel for how little of the galaxy we have actually looked at. We have looked at thousands of stars, and yet it is just a drop in the bucket. We have hardly touched the cosmic haystack. We want to move on now to 1,000 light years from the sun, several thousand. And to do that, We at SETI Institute are constructing a radio telescope just north of Mount Lassen in Northern California. It will use 350 small antennas using dishes as you see here. They're each 20 feet in diameter. Here you see actually 10 dishes nested together being carried from the manufacturing plant in Idaho Falls, Idaho, all the way to Northern California on this truck where there's this tilting bed because when you go under, it needs to be tilted like this to not be too wide for the highway, but it's now too high to go under underpasses. And so it has to be tilted up horizontal, and you have to bring the police and close the road whenever you go under a low overcrossing. And here are two of the dishes already in place at Hat Creek in this project, which is a joint project with the between the University of California at Berkeley Radio Astronomy Lab and the SETI Institute. And here's some really happy people recognizing, hey, the dishes actually move and focus radio waves the way they should. And here's a picture with 3 dishes in place. And this is presently we're in the process of making a 32-dish array, but the eventual goal is 350 antennas in this system, which is called the Allen Telescope Array, named for Paul Allen, one of the co-founders of Microsoft, who has provided major funding to the project. This is what it will look like if all goes well and the funds are raised. We do not have all the funds in hand yet. This is what it will look like in the year 2007. And what we will use to continue the search. The search will go on at Arecibo. Arecibo cannot look at the whole sky, and in particular cannot look at the center of the galaxy, which is one of the more promising places. The Allen Telescope Array can look at the center of the galaxy and examine much more of the galaxy than the Arecibo telescope. The Arecibo telescope has more sensitivity, but the Allen Telescope Array will be able to look at some of the prime places in space. So where do we stand? We've learned that there were some things we were badly wrong about 44 years ago. We've learned a lot more about where planets can be habitable, and that there are far more than we ever imagined. And in all other respects, our assumptions or guesses 44 years ago have turned out to be roughly correct, and that in fact we can expect a very large number of detectable civilizations in space. So we should continue. If we do not search, we lose an opportunity to enrich the world with a wealth of new information, and we'll lose almost nothing in material value. It doesn't really cost a lot to carry out these searches, at least not in the grand scheme of things. Some people think it costs too much. This is just to say that's not true. The opportunities are too great. The potential benefit far exceeds any reasonable cost, which is, in any case is minuscule. If we do search, we may enrich knowledge and philosophy without bounds. It will cost us relatively nothing. All of SETI in the whole world costs only a few $1 million a year. Very small compared to other major scientific projects. And perhaps most importantly, scientists, like all people, have their dreams. We all need dreams of a better future, of accomplishing good things, of having a better life, and we will keep alive our dreams of learning of other intelligent life in space.